Welcome to The Explainer. Today, we're doing a deep dive into the absolute workhorse of plant engineering. I'm talking about a material so fundamental it practically holds our entire industrial world together. We literally see it every day, yet we rarely understand the incredible microscopic balancing act that makes it so incredibly useful. But, as we'll see, even the greatest materials have their fatal flaws. So let's just jump right into it.
I want you to just imagine something for a second. If you look at massive chemical plants, towering refineries, or those sprawling industrial facilities, what's the one foundational material that forms the skeleton of it all? What's the core ingredient actually building our modern world, taking all those massive pressures and structural weights? Well, the answer is carbon steel. At its core, carbon steel is an alloy. It's a really specific, carefully controlled blend of iron and carbon. This is the foundational, ubiquitous material in industrial construction. It's really the true hero of our story today. The go-to material engineers reach for before literally anything else when they're designing a massive project. Here's our roadmap for this explainer. We're going to look at the plant engineering workhorse, the iron-carbon recipe, and the trade-off of strength versus toughness. Then we'll uncover the dangers of cold and brittle environments, the rust problem, and finally, how we engineer around those flaws. And hey, don't worry if you're a beginner to metallurgy, we are going to break this all down step by step.
Moving right along to the plant engineering workhorse. Let's set the stage for why this material is relied upon so heavily across the entire engineering industry. Now, while there are certainly a ton of exotic, high-tech metals out there, carbon steel is your everyday hero. It is absolutely ubiquitous. It forms the literal skeleton of process plants. When mechanical engineers design equipment, they use carbon steel for massive pressure vessels, extensive piping networks, and those huge, heavy structural supports. And why? Well, because it strikes the perfect balance. It's highly cost-effective and incredibly adaptable. You get a massive amount of structural integrity without totally breaking a project's budget. Next up, the iron-carbon recipe. Because to truly understand why it's so adaptable, we really have to look at how it works on a microscopic scale. Check out this concept of an interstitial solid solution. So think of pure iron as a grid of large, uniform atoms. By themselves, they can slide past each other relatively easily, which actually makes pure iron kind of soft and not very useful for heavy construction. But when we add carbon, a kind of magic happens. These tiny carbon atoms fit perfectly into the empty spaces, the interstices, between those larger iron atoms. It's exactly like adding flour to a sauce. Just a little bit of carbon thickens and strengthens the iron matrix, locking the iron atoms right in place so they can't slip anymore. But here's the absolutely crucial point. Precision is everything. In industrial plant engineering, most of the carbon steel we use contains less than 0.4% carbon. Now, that sounds like a tiny, almost insignificant amount, right? But as you'll see in a moment, adding too much carbon fundamentally changes the metal's entire personality. It is a super delicate balancing act. Which brings us to strength versus toughness. That balancing act introduces the core conflict of the material. To really get materials engineering, you have to grasp the difference between these two opposing physical traits. Strength is the material's ability to withstand heavy loads and high pressures without bending or deforming. Toughness, on the other hand, is its ability to absorb sudden impacts or energy without completely shattering. And in carbon steel, these two traits are constantly at war with each other. This graph illustrates that conflict perfectly. It's kind of like a map of metallurgy. Along the bottom axis, we're tracking the percentage of carbon added to the iron. Now, notice how, as the carbon percentage goes up, the curves for tensile strength and hardness rise sharply. The material gets way stronger and harder. But look at the curves sloping downwards. That's elongation and impact resistance, which is basically how we measure toughness. They absolutely plummet. The more carbon you add, the stronger the steel gets. Sure, but it becomes significantly less tough. It loses its ability to stretch and absorb impact, becoming super rigid and fragile. So let's talk about the danger of cold and brittle environments. What actually happens when this material gets chilly? You can see the two greatest field vulnerabilities anchored right here. On the left, we have a catastrophic, brittle fracture of a pressure vessel. The metal has literally just torn open. And on the right, severe, flaking corrosion eating right through a pipe. Let's dissect that terrifying fracture on the left first, because it is directly tied to environmental temperature. We call this the temperature trap. As the temperature drops, the metal's internal structure becomes rigid. Carbon steel loses its toughness dramatically in the cold. So instead of yielding, bending, or stretching under the massive internal pressures of a chemical plant, it shatters.
It literally fractures like glass in freezing environments. This phenomenon can turn a robust, pressure-holding vessel into a highly fragile hazard just because the weather changed or the fluid inside got too cold.
Then we have the rust problem. Because the cold isn't the only enemy out there, we also face a much slower, relentless adversary. Corrosion is a chemical oxidation process. It's exactly what happens when the iron inside our carbon steel reacts with moisture and oxygen in the environment to form iron oxide, which, we all just call rust. Unlike some other materials that might form a nice protective layer, carbon steel is completely exposed. This chemical reaction just continuously attacks and eats away at the surface of the metal, slowly weakening the structural integrity of the plant over time. Engineering around the flaws. With all these issues, why on earth do we still use it? Well, this is where brilliant design steps in to overcome those physical limitations. 3 millimeters. I know, it doesn't sound like much, but that number is literally a magic constant in plant engineering. Because engineers know carbon steel will inevitably rust, they outsmart it. They design pressure vessels and pipes to be exactly 3 millimeters thicker than the stress calculations actually require. This extra padding is known as a corrosion allowance. It acts as a sacrificial layer. Over the entire lifespan of the plant, the rust safely eats away at this specific 3 millimeter barrier, leaving the actual required structural thickness of the steel completely untouched and perfectly safe. So, what's the ultimate real-world toolkit engineers use to protect carbon steel and ensure safety? First off, they strictly limit that carbon content to under 0.4%, just to maintain that vital toughness. Second, they add that brilliant 3 millimeter corrosion allowance we just talked about to account for rust. Third, they apply heavy-duty industrial protective paint to block moisture and oxygen from ever reaching the metal in the first place. And finally, if the operating environment is just way too freezing cold, they simply don't use carbon steel at all. They'll switch to a different alloy, like austenitic stainless steel, because its unique microscopic structure retains its toughness even at extremely low temperatures. It really all comes together in this brilliant thought. Engineering is the art of balancing material imperfections to build a perfect world. I mean, carbon steel is far from perfect, right? It rusts and it gets dangerously brittle when it's cold. But by deeply understanding that microscopic iron-carbon recipe, engineers can harness its incredible strength and affordability, completely neutralizing its flaws through smart design. Which leaves us with a pretty fascinating question to close on. If we can engineer around the distinct fatal flaws of carbon steel to build the massive modern industrial world around us, what other imperfect materials will build our future? Keep that in mind the next time you look at a towering industrial structure. Thanks for joining me on this explainer, and keep exploring.